let's continue this. So we have this input and instructions. So in an imperative way, let's say, how do we do this? Hang on.
What is instruction?
Instruction is of this structure.
Is it an object?
Map.
Yeah, it's an object. Can't map it.
We can't map it?
It's an object, not an array.
Oh, yes, like object or keys, something like that.
Yeah, let's say imperative, not function programming, like normal programming.
Normal.
Yeah, how do you write it? You got to input, and you will go through them one by one. How do you do that? The simplest solution, just hard code or whatever, hard code keys you want.
Input 0.
Okay, so you have, well, again, we don't do mutations here. So first you do multiplication, right? Yeah. So you say multiplied equals to input
dot multiply
times, right? That
instructions multiplied.
Yeah, instructions dot multiplied by.
Yeah. And then the second one is edit equals to multiplied plus instruction dot edit by, right? Yeah. So the third line, I'm just going to write this out because it's important for the thing following this. Divided equals to edit divide by instruction divide by, yeah, and then you return this divided, yeah, that's it, right? Enough. Okay, let's just get rid of this one. We all know what's going on here. All right. Let me draw two columns here. One is the value we'll produce. So the values. That will be the multiplied, added, divide. So going through lines of code, you have different things being produced. And then here is what happened. Which we're acting like a log of what does this function do. Okay? So for the first one, let's say the input is 1. And remember we have multiplied by 2, add by 1, and divide by 3. Yeah, okay. So the value here, on this line, it produced 2. Yeah? And what happened is basically, in English, is just reading that, right? So it's just 2 has been, multiplied by 2. Okay? So this is the input, this is what happened. And then here, the edit will be 3, and 1. Let's write this. Okay. There's 2 plus 1. This is the operation which happened, and then here will be just 1, and that's the operation. Okay. Now, I can say now that don't look at this one. Don't look at that. If we have a functor encapsulate an integer, then we are doing those operations on the value encapsulated. That's not correct. Let's say you have a trivial functor ID. ID is a functor. It's remember we have this functor before. Right? Okay, so let's maybe use another example. Array. Let's say you have an array of integers, and if you only have one integer inside, starting with 1, then you're sort of mapping it with composition of those functions. Right? If I write it out, would it be map compose multiply by 2 plus by 1 and divide by 3. Right? And then you put a functor here, array which input is 1. Sorry, it needs to be reversed. Yeah. Okay, so times 2 plus 1 divided by 3. Okay. Now, array gives you the ability to loop through things inside. If this is a trivial functor, which means it just encapsulates a value, it's just a container that does nothing else, then it's ID functor. The map will just map the value inside, and that's it. But for array with only one element inside, it's kind of the same thing. So that means this is the value that inside a particular functor you can map through with those operations. But those numbers of those operations are coming from another input. They're not fixed. So that's coming from this side. Remember the radar monad we were talking about last time. That is what coming from the radar. Is those things. Environment, yes. Okay. If we treat it like this, then we're looking at a radar monad, which is mapping the value like this. If we say we're not only reading it, but we actually logged what happened, that is, use a different color. That is the entire thing here. That means we are writing a log as well for every single step. So what happened at every single step was we're reading from an environment, we're doing a particular operation generating a value, and then we log it out like this. If we're doing that, then we're looking at a state monad. Yeah? We'll talk about the reader and the writer. Then state is you can read and you can write. Just bidirectional. Yeah? So we're looking at code of how do we convert this into a way that uses state monad. Can you see that? Yeah. This one? All right. Okay. So let's go through this example. I think it's exactly the same as this function. Now we have 3 functions, takes 2 parameters, current. Yeah. Add, multiply, and divide. Okay. For radar, you use ask. Right. I was wrong. I put get there, but it was radar.ask. Now for state, you do exactly the same, but slightly different name, change of name. So state.get. Now state.get is of type state. It encapsulates. You need to run it as well, like the same as radar, and pass environment when you run it. So it's a functor. It's a monad. That means you can map it, you can chain on it. Here, what I do is first after get, you get the environment in your functor. So after get, the environment, the value here will be in your environment. Right? So the instruction will be here. That is inside this function. That means the state here is the environment. And the state has add by, right? The add by. Yeah. And then I call this add function with whatever the A, which is the input, and then the thing I read from the state, which is add by, get my result. And then I use the put method on the state to say, now I return a type which is of state, but I log it. The put is to say, whatever state you have there, added a key called edit, a new key there called edit. The value for that key is whatever the value we added on. Yeah. So that means after this line of code, remember we have stay here, right? Stay here, and input A, and then after we put, we have this thing. We have something times some 2 already happened, so we can log it. And then the map to say, because remember the writer, when you write, and your value here becomes empty. Remember the writer monad, once you write, your functor does not encapsulate any value. So in order to get it back, we say map always. After this line, you have the 2 here. Okay. So we do the same for multiply with state. We'll do the same for divide with state. Same pattern, same concept. Let's go through divide maybe. The same, getting the environment, which give me the state, put the state into the value column, and then the value column dot divide by would be the environment divided by, which is this number 3 in this example. And then I put the result into the state as a log here, and then map to produce that value again inside the value column. So that's those 3 functions. And then last time we'll talk about composition on Kleisli arrow. Remember that a function takes a plain value, returns a functor of value. That is, in this case, that is right here then. All those function has the type signature. Just writing so add with state takes integer, that is the A. Return stay monad, and here's add by, that's integer, multiply, that's integer, and then we have like divide by, that's the integer as well. Let's use Haskell notation. Yeah. And this is the state. This part is the state, right? And then the value encapsulated is the integer as well. So this part is a functor. If I just use one letter to replace this thing to annotate the state is just E here, this one is a functor. Remember last time we say reader environment A, this one is a functor. Right? Not the reader itself, the reader E is a functor. Here the state E is a functor. Now a plain value, well a value as an input, and the functor here is also monad as an output. Those kind of function will call that Kleisli arrow. For Kleisli arrow, you cannot compose them directly. Remember that? Let me just go through that again. So if you have A to MB and B to MC, the M is a particular monad. It can be a list, right? Let's say this example. You cannot simply compose those two functions. That means doing, if this is F, this is G, by doing G after F, they don't compose. Correct? Yeah, because there's an array there, stop you getting that B, right? If you use lambdas compose K, then they compose. Here is the same. With this type signature, actually they all this type signature, right? That means you're looking at that scenario again, a Kleisli arrow composition. That means you can use compose K with those three things. Again, state has a run on it. When you run it, you pass the initial environment. Same like radar. Right? The radar is you pass the environment at last. Here, state, you pass the environment at last as well. Let me just run it, see if it actually works. Ah, here you go. I ran it before. A state encapsulates a tuple. The _1, _2 means it's a tuple. It's a tuple. Right? This is _1, this is _2. This is what you write into your state, or together with your initial environment. This is the value inside your functor when you map through, when you chain them. So the final value after these three operations is 1. Right? That's the final value. And we logged those three things as well. Remember, for the divide with state, for example, we use put to do divide and assign a value of the value has been divided. The same with multiply with state. We put multiplied into the state. So that's why those three things in your state as well. Okay. After you run it, because this is the composition of all the operations together with initial input 1, then you have the result like that. Okay. So it's a combination of reader and writer. Cool. Okay, let's try to implement this function. Apply with state, multiply with state. When you do state.get, it's a functor encapsulate your environment, your state so far. You could already read and write into it already, but whatever that is, you get that as the value inside this functor after state.get. Right? And in order to operate on things inside the functor, what do? You map, right? You can only get things inside the functor using map. Okay, so when map, because I have the get before, that means I'm mapping the state here. Yeah. That means in order to do multiplication, we have two things, right? The input itself, which is the A here, right? And the other thing comes from the environment. The environment is the state here. State dot multiply by, and that's my result. That is my result 2 here. But inside here, I need to do two things. One is I need to change that value actually become a 2. Because I just did a calculation, didn't return it inside math, right? The second thing is I need to log it here. So first what I do is, how do I log it? I need to return a state again because I need the state to log it. So dot put, what do I put? I have the original state. It's like a reducer, right? You have the original state, which is the state, and the key I'm getting in there is multiplied, and let me indent it. Yeah. And the value is the result I want to put in. If I just return this, what do I get? I get that, but no value here. Same as writer, when you log, your functor contains no value. That's how state and writer works. In order to actually do that, to put a 2 here, to do that, you need to say, okay, currently I have no value. I have a log to already written, but I have no value. So I need to map again to say, always return this result. Then I have 2 here. If you don't do this, here will be empty. Yeah? Because I return, look at this function. I return a state, right? A state type. State E is a monad. That means I cannot use map. Map does not take Kleistli arrows. That means I need to use chain. Normally, this is how you write it. If you start to work on the functor, you write map and you transform your data. And in the end, you think you need another monad as a return value. You change the map to chain, basically. Does that answer your question? Yeah? All right. Okay. So let's take a break. Yeah, cool. Thanks.